Welcome to my presentation about the 11th problem of the GYPT guitar string. My name is Nils Wagner and I'm from the team Victorious. The problem. The periodic force is applied to a steel guitar string using an electromagnet. Investigate the motion of the guitar string around its resonance frequency. The keywords are periodic force, steel guitar string, electromagnet, motion and resonance frequency. There are two different kinds of motion. One, the motion of the whole string, and second, the motion of one point of the string over time. Now to the experimental setup. We have a string which is made of a ferromagnetic material and is fixed between two fixed points. One point is a Newton meter to detect the tension force. Then we have an electromagnet which is placed right next to the string and run by the function generator. As sensor we have an induction coil with a magnet, and the signal gets amplified in the amplifier and then to the vernier converter where it's converted to a digital signal, and then we can investigate it at the laptop. Now to the electromagnet. The electromagnet works that the current flow in the coil generates a magnetic field. We can control this magnetic field by controlling the current and the frequency of the electromagnet. Now to the experimental setup. We have a function generator, a Newton meter, an electromagnet, a string, an induction coil, an amplifier, and LabQuest as vernier converter. Then a close-up of this setup is that the string is here, the induction coil, which we can move freely, and the electromagnet, which is perfectly placed in the middle of the string. Now to a video of an oscillation. Okay, and now to the parameters to be investigated. At first, we need to describe the motion around the resonance frequency. And to determine the resonance frequency, we use the term for calculating the eigenfrequency. But now the question is if the eigenfrequency is equal to resonance frequency. And in our experiment, it's nearly equal because the tension force which gets changed is only so minimal that at those lower amplitudes, the eigenfrequency is equal to the resonance frequency. So we can use the formula for calculating the eigenfrequency. In this formula there are certain parameters. One, the string diameter and material density. Those are string specific. And then we can only change them by changing the string. Then we have tension force and string length. Those are parameters we can change by changing our experimental setup. Now to the generation of the oscillation. The electromagnet pulls the guitar string by magnetizing the guitar string, and a magnetic field acts on the guitar string and pulls it towards the electromagnet. Yeah, and because we have a frequency of a sine wave, with which we run the electromagnet, the poles of the electromagnet get switched over time. But this doesn't affect the side that much because only the relative force of the string is important for the side. So the frequency of the electromagnet must be half of the eigenfrequency. Now, how does the string move? You can basically say it like in 5 points how the string moves, and this process repeats itself periodically. So the first point, the string is attracted by the magnetic field of the electromagnet. So a magnetic force is acting on the string and pulls it towards the electromagnet. Then the restoring force acts and the magnetic field decreases. So the restoring force is bigger than the force acting on the string by the electromagnet, and the deformation energy gets transformed into kinetic energy. So the string has a certain velocity. And then the restoring force acts again, but this time in the other direction, and the magnetic field increases. So the string gets pulled back to the electromagnet. Then again, deformation energy gets transformed into kinetic energy, and this process, as said, repeats itself periodically. Now, to describe the motion of the string, it's important to know how the string can move. And because we have two fixed points, the string only can move in certain ways. One, the fundamental oscillation, and the harmonics. The first, second, and third harmonic. And to describe the motion of the string, we need to know on which proportions each harmonic is moving the string. Now to the data collection with the copper coil. We replaced our sensor next to a string section, and when the string moves, because the string is magnetized, the magnetic field inside of the coil changes, and thus an electric current is measurable. And because of the amplifier and the Vernier converter, we can measure this at the laptop. And the measurement of this looks like this. This is an example measurement, but this is not quite the movement of the string, because also the electromagnet induces a certain voltage in the sensor. So as you can see here, we have overtones, and we have but this is not given by the side, this is given by the electromagnet. So we need to filter it out. And therefore we use the Fourier transformation, and the Fourier transformation states out that every original function can be broken down into certain sinus functions, and by adding them together you can get the original function back. So we did this to get the proportion of different generated frequencies in the coil at different distances. So as you can see here, we have the proportion in percent and the frequency in hertz. As the frequency of the magnet is at 31 hertz, and the fundamental oscillation is at 6.2. So the frequency of the magnet is the exact half, as I stated out earlier. Then you can see the first harmonic at 142 hertz, and the second harmonic at 168 hertz. So those are exactly like the double and the 4 times of the fundamental oscillation. As you can see, the proportions differ really hard, because you can barely see the second and you can't even spot the third harmonic. So you can conclude that the string moves proportionally more in the fundamental oscillation. So the movement of the string is more of a fundamental oscillation. Then we did that as different distances, and the closer you go with the sensor to the middle of the string, the bigger the proportion of the fundamental oscillation is. So now to the influence of the string. I used 2 different strings to detect if there are differences in the proportions of the amplitude of the harmonics in the string. So I did this in an experiment, and as you can see, the proportions of the harmonics are nearly the same. So you can state out that the string, that the A string and G string have similar proportions of harmonics. Now for the measurement of the amplitude, I used a pen and put the pen at the resting string. Then I measured it, and then I let the string move, and then I moved the pencil so right next to the string, and as soon as the pencils touched the string, I measured the amplitude. So that's the way how I measured the amplitude. Now for the theory, I used the D'Alembert equation, and this equation is a homogeneous wave equation to describe undamped oscillations. Contrary to a guitar string, when you pick a guitar string, it gets damped over time because it loses energy due to friction. In our system, this friction loss is equal to the energy we put in the system while using the electromagnet. So we can describe our motion as an undamped oscillation. So we can use this equation. After transforming and after inserting the formulas, you can get the following equation, which is the equation of motion, which describes the undamped oscillation of an idealized string with certain harmonics. Therefore is n the number of harmonic, and an the amplitude of each harmonic. We can calculate the amplitude of each harmonic with the proportions given by the Fourier transformation. The string length is given by the experimental setup of ours, and the period of oscillation is also given by the experimental setup of ours and also by the string. So now for the representation of movement. We plotted the string movement while using the equation for the movement, and it looked somewhat like this. And this string movement is for those parameters. And for example, and the amplitude of the first harmonic is at 8 millimeters. So, and as you can see, it's an addition of the fundamental oscillation and the first harmonic. Yeah, now to the representation of the movement in general, because because now I described the whole movement of the string, I want to describe the movement of one point of the string over time. So I transformed the equation and set the point at exactly a quarter of the length of the string, so that the amplitude of the first harmonic is the biggest. So now I plotted 3 graphs. One's deflection in meters over time, and then the velocity of the string in time, and the acceleration of the string over time. So as you can see, it really describes well how the string moves. So now to conclude my presentation, I gave a fundamental explanation on how the string moves, because the electromagnet makes the string moves, and how harmonics work. And then I made measurements for different parameters. I changed the string, then I changed where the center is, and all kinds of stuff. Then for those I did the Fourier transformation, and I got the proportions of certain harmonics. And after that, that gave me a good value of representation of the string movement, so I can model the movement of the string, which answers the problem question.